Okay, good afternoon, everybody, and thank you for joining us at today's Grand Round sessions. First of all, I'm just going to get us started with a few housekeeping tips. Number one, I just wanted to encourage all of us who are here in person as well as online to be as present as we can, despite the very enticing invitations from all of our points of distraction. Thank you in advance for that. If you do need to take a call or answer a page, we would just ask that you step out to do so. The second is that your presence here is some of the best parts of our engagement with our speakers that we invite here to the department. And you have an opportunity at the end of this session to ask questions about what you're hearing today. The same is true if you're joining us online. So we would encourage those online to use the Q&A function at any point during the session to let us know what's on your mind. I'll be moderating that discussion at the end. So if you ask a question and we don't answer it right away, please know that I have seen it and I'll make sure to work it into our discussion at the end. And if you're here live, please know that I try to be exquisitely fair in balancing live in the room questions with online questions. But I will invite you all to go to the microphones that are on either end of the room to ask questions live. Last but not least with housekeeping, we also invite your feedback both about this particular Grand Rounds and the content, as well as the Grand Rounds experience in general. For those of you here live, you'll see that QR code come up and is also available, I think, on printouts before you leave. And for anybody who's registered online, you'll receive that, that evaluation link in your email. Those evaluations are required for you to receive continuing education credit. So if that's important to you, you want to be sure that you complete that as well. But thank you in advance for your feedback. Now on to the good stuff for today. I'm very excited. It's my pleasure to introduce Dr. Laura Schulz, a distinguished professor of cognitive science, whose work has deepened our understanding of how children learn and think. Dr. Schulz earned her bachelor's degree from the University of Michigan and her master's and PhD in developmental psychology from the University of California, Berkeley. She's now a professor in the Department of Brain and Cognitive Sciences at MIT, where she leads groundbreaking research on early childhood cognition, learning, and causal reasoning. She's also Associate Department Head for Diversity, Equity, Inclusion, and Justice in the Department of Brain and Cognitive Sciences. She's a PI or co-PI in several large grants funded by the NIH and the National Science Foundation, and has a long track record of foundation-funded grants as well as a number of National Society and Foundation awards over the last 2 decades. Throughout her career, Dr. Schulz has authored over 120 peer-reviewed publications. Does that sound like a right number?
You know better.
I mean, I do as of 11:30 this morning, over 120 peer-reviewed publications, contributing extensively to our understanding of cognitive development. Through her work, she's explored how children, despite limited experience, can rapidly acquire knowledge, form hypotheses, and make sense of an incredibly complex world. If you're an adult in this room, you probably wish for those things too. I'm sure we can learn lots about her work, even as it extends across the lifespan. Her research focuses on the processes that support exploration, inquiry, and discovery in early childhood, and contributed to topics including causal reasoning, social cognition, emotion understanding, moral reasoning, and the connection between play and learning. Dr. Schulz's research has broad implications, not just for developmental psychology, but also for education and our broader understanding of human intelligence. Her insights challenge us to rethink learning, not as something that happens only in the classroom or in residency or internship or fellowship or any other training program here, but as a natural, intuitive process driven by curiosity and reasoning. So with that, I'm going to remask and invite Dr. Laura Schulz to the podium, and please join me in welcoming her.
Thank you for that very kind invitation, and thank you for inviting me here. I'm incredibly excited to be here. And I've been thinking a lot about the relationship between the work that many of you do in this room, helping and trying to understand and alleviate the suffering of some of our most vulnerable young people and older people. And work in my field of cognitive science. And I think especially that our work has a lot to learn from the work you're doing, because in my work, we focus on rational inference, and we hardly ever think about the ways that that might go wrong. So I'm excited to be here today and to learn a lot from all of you. As I was saying to some folks at dinner last night, I think I might be a little bit the comic relief of your grand round circuit, because my work focuses on healthy, typically developing young children and basically looks at human flourishing. So I look at children in my lab primarily as a method. Because I use children as a method for understanding how human minds work. Because as far as we know, in the known universe, there's only one organism that solves all of the hard problems of cognitive science. Problems of face recognition, natural scene understanding, language acquisition, causal reasoning, motor planning, theory of mind, emotion understanding, and moral reasoning. And that is the human child in the first few years of life. So if we're going to understand how minds work, we need to understand what's going on in the minds of developing children. And we live in a super interesting world today, because we live in a world where we can engineer intelligence to a first approximation lots of ways. So we have machines that can almost kind of sort of drive cars. We have large language models that can write college application essays. We have AI that can beat the best human players at 1,000-year-old games, and the AI that is the engine of countless lucrative corporations. And it's an interesting fact that a preschooler can't drive a car, they can't write a college application essay, a Go piece is a choking hazard, and children have almost no market value. And yet human children can solve all kinds of problems that today's AI cannot. When you walk into your home to see your 18-month-old, you do not need a password. Children can solve problems of motor planning and dexterity that today's roboticists can only dream about. Children can't look 20 moves ahead and go, but they can imagine possible and imaginary and counterfactual worlds literally as child play. And children can't recognize a million faces with high fidelity, but they can look at a single human face, even one with a deeply non-canonical emotional expression, one that Google Images, for instance, might say expressed anger or frustration or was falling asleep, and infer all kinds of much more accurate things about what that person is thinking and feeling. So in my work, I try to bridge the gap between computational models of learning that tell us how such learning might be possible and the actual behavior of young children. And basically, I try to understand how children solve the problem of induction, how it is that they learn so much from so little so quickly, and how it is that they draw such rich, abstract inferences from such sparse, noisy data. And I've come to understand that the way I see cognitive development and child development in my field is maybe a little different from the perspective that many of you have in that work. And full disclosure, my entire knowledge of this field comes chiefly from my own son there, Henry Filofsky, who's a psychiatry resident in your field. But I realize this might be in tension with some ideas about children. For instance, don't children learn from patterns of reinforcement over time? And aren't children only sensory motor learners at birth? And aren't children concrete thinkers? Doesn't it take until almost adolescence to engage in abstract thought? So before I begin talking about my own work, I want to spend just a few minutes talking about the status of these theories in my field, because there's no question that these ideas about behaviorism and Piagetian theory have been enormously influential. So behaviorist theories emerged in the early 20th century, and to this day, I don't know a single animal lab that isn't using conditioning models. And in practice, for instance, many very hard to reach children with autism, applied behavioral analysis, which derives some of these ideas, can be used to teach children really critical life skills. So it's very important, it's very valuable, and it works. I can condition my undergraduate class to start reaching out their hands every time I shake my keys. And about 7 trials if I toss candy at them each time I shake my keys. You know, the whole class will go like that. So it works, and it's very effective. But it became apparent in the middle of the 20th century that it was an inadequate account of learning, even in animal models. even for animals. So, for instance, it turned out that rats, and this led, by the way, to essentially the demise of behaviorism in a lot of science and the cognitive revolution. So it turned out that even rats would learn all kinds of things they weren't actually reinforced for. So they would get cheese in a couple corners in the maze, and they would learn the entire map, and they would be able to take shortcuts. Researchers refer to that as latent learning. Today, we just think of that as maybe learning. The beauty of behaviorism was that it was and is a computational model of learning. You could kind of precisely figure out the reinforcement schedule and say many, many things about behavior to a point. Because it turned out that the math that would predict how many times a light would predict a shock or a smell would predict nausea didn't work if you flipped those stimuli. No amount of lights would get the rat to learn that it would be nauseous. No amount of smells would teach the rat that it would learn to get a shock. So some associations were learned much more readily than others. But there were also theoretical debates. Noam Chomsky had a big debate with B.F. Skinner and pretty conclusively put the kibosh on the notion that you could learn natural language from reinforcement. That isn't how children were learning the rules of grammar. This is where Chomsky came up with his famous line about the poverty of the stimulus. There just wasn't enough input available. And then, of course, really importantly, Alan Turing came up with an entirely different way of thinking about how you might do reasoning and inference that had nothing to do with reinforcement and everything to do with symbol manipulation. And that is, of course, much of the legacy of where we are today. Of course, there was one really amazing, groundbreaking researcher who was never a behaviorist, and that was Jean Piaget. In an argument with B.F. Skinner, he said, of course we learn by associations, but that answers exactly nothing at all, because the question is, which associations do you learn from the infinity of possible ones? And Piaget, of course, you all know, and he's most famous today, I think, for two key ideas, although he wrote hundreds of books and literally founded a field. But he's certainly known for this idea of constructivism, the child as an active learner, and a child who, in his words, was assimilating and accommodating evidence. But in our words today, we might say was integrating prior beliefs with new evidence. And for any of you familiar with Bayesian computational models, that was an incredibly insightful and really influential idea. Jean Piaget, of course, was also known for stage theory, based on observations largely of his own children, certainly at the early ages. And many of you know these theories. I don't know what to do about the transcript blocking the things, but you all know stage theory. So, baby star sensory motor learners, formal learning develops relatively late. And I have a cross out there and a green box because constructivism I think remains an enormously influential view in my field, but stage theory does not. In fact, stage theory largely collapsed starting in the 80s in the work that I do. And that is largely due to an infancy revolution. So the infancy revolution involved a series of papers, now hundreds and hundreds, showing that actually babies understood many things way before Piaget had believed. Again, Piaget's measures were largely reaching measures. They turned out to be measures that were very dependent on performance limits, right? How well can babies engage in motor plans? And Piaget did not have access to a really powerful piece of technology, the video camera. And when you could use a video camera, you can watch babies and you can bore babies. You can show them the same thing over and over and over again. For instance, you could show them a drawbridge going back and forth 180 degrees. And then you could hide, let's imagine this was a much bigger drawbridge, an object behind it. And if babies don't represent objects out of sight, then they should still be bored when that thing goes 180 degrees. But in fact, babies recovered their interest and looked much longer. And they did not look when it stopped. Please. I'm so sorry. I'll try. I'm used to walking around the class, but I will stay much closer. Babies not only represented hidden objects, they represented their properties. They knew how tall they were. They knew how rigid they were. They knew whether they were compressible. They also understood things like the objects were solid. That the objects were solid and they couldn't pass through walls. Not only that, babies understood some things about early number representations. If you hid one object behind a screen and you added a second, babies were surprised if you dropped the screen and there was only one. They expected two. If there were two objects behind the screen and you removed one, they were surprised. If you dropped the screen and there were two, they expected only one. It wasn't just objects and number. Oh, by the way, they also represent abstract number concepts like large approximate numbers, the difference between 8 and 16 dots, regardless of area and continuous extent. It's not just babies. Birds, we now know, can keep track of the number of eggs in their nest. Newly hatched chicks have object permanence. Many animals can do approximate representation. So a lot of these early emerging systems are evolutionarily ancient and phylogenetically old and ontogenetically early. So they emerged quite early. But it was also true of social behaviors. Babies understood goals. They understood that a reach through space was not just a reach through space, it was directed at a target. If you changed the trajectory but retained the goal, babies didn't think that was that interesting. If you kept the trajectory but you had switched out another goal, that they were much more interested in. So on and on. I'm going to show you just a single example in a little bit more detail to make, I think, the important point that the current view in my work is actually almost the opposite in this respect of what Piaget believed, which is that abstract inferences emerge first. That what babies have early are very large abstract framework concepts, and then they have to fill in all the details. I sometimes illustrate this with my students by asking them how many of them think I have a spleen, and they all raise their hands. And then, a lot of my students are pre-med, and I say, how many of you know what a spleen is and would like to come to the front of the class and explain one to me? And shockingly few of them want to. So we understand a lot of things in sort of abstract terms, but we don't understand the details. Turns out that's true of babies. So this is a really beautiful, fairly recent study by my colleague, Elika Bergelsen. And she showed babies, 6-month-olds, objects on a screen, and she used an eye tracker to look at where they looked. And she would show them, for instance, a bottle and a spoon and say, look at the spoon, look at the spoon. And guess what? The babies look at chance. They don't know which of those objects is a spoon. But if you compare instead the spoon to, say, a baby, right, a living being, right, and you say, look at the spoon, babies look at the spoon. It also turns out to be true that if you say, look at the bottle, babies look at the spoon. They don't know the meaning of the word spoon, but they have a hierarchical abstract representation of the category structure. And then they begin filling in the details. And she showed this across very many categories, that if there were related pairs, the babies had no idea. If there were semantically unrelated pairs, the babies knew where to look. I find this work reassuring when I forget words all the time, which is I frequently mistake the word. I rarely mistake the category. So for instance, I might call Henry by any of his siblings' names, but I'm not going to call him a spoon, right? So many of us are familiar with this. Okay, so these ideas, behaviorism, again, and Piagetian theory continue to be influential, but they've radically changed. And in some ways that shouldn't surprise us, because this work is now almost 100 years old, which is to say this was written, these ideas were crafted before the invention of penicillin. So if you imagine what's changed in other medical contexts, it might give you a sense of how much our science of understanding human minds is changing as well. So what I'm going to do here is do a kind of whirlwind tour of a few studies from my lab that provide a little more texture for why we think babies are such powerful learners. And I'm going to talk about kinds of problems that we think we might really, oops, this is a very fast to react system, that we might really care about. So knowing when problems will be easy and hard, making decisions about how much effort to exert, understanding goal-directed action, and understanding it's blocked, but why other people might feel the way they do. So understanding something about emotion. So I'll go through these very quickly, maybe mainly illustrating the logic of the design, but I'm happy to ask questions about the methods and the data in more detail. Okay. So this is one of my favorite studies. It's a few years old now. I like to call it the black box study because at MIT we have physics and envy, but it's a very embarrassingly simple study. So we gave children a box and we said, okay, we're going to put some marbles in this box. We're either going to put in 9 red marbles or 3 green marbles, but we're going to do it behind a screen so you can't see. But afterwards, you can shake the box and find out what's in it, right? So very simple. Kids get to shake the box and guess, oh, it's a lot of marbles. Let's say that is 9 marbles that are actually in the box. And then that's very easy. But with another group of children, we might do the same thing, but we say, we're going to put in either 9 red marbles or 8 green marbles into the box. You get to shake the box and find out what's in it. And again, children, sorry, in this case, these are children, get to shake the box. And if they're shaking that box based on what they see and feel, it's sort of concrete, tangible properties, it's exactly the same box. But if children are shaking the box not based on what they hear, but based on an alternative hypothesis about what might be the cause of that sound, what else might be in the box, 9 versus 8 is a much harder discrimination problem than 9 versus 2. So they're only ever hearing 9, but they should shake a lot longer if they are trying in their minds to simulate what 8 would sound than if they're trying to simulate what 2 would sound like, and the contrast. So we're at MIT. We can do fancy things like put lots of marbles in boxes numerically. We can also actually model children's internal representations of number, right? So we know something about the actual discriminability between each of these contrasts so that we know that 4 versus 2 is a little bit harder than 7 versus 2, but not as hard as, for instance, 9 versus 8. So we tested children in 4 waves so that children only ever saw 4 contrasts, but they got 16 contrasts over the course of the experiment. When I say this experiment is simple, let me show you how simple.
All right, so remember, it could either be the 1 green or the 8 red, and when you know, you can put your answer right there. So go ahead and play. 1, okay. All right, so remember, there could be 4 yellow or 5 blue, and when you know, you can put your answer right there. So go ahead and play.
5.
All right.
Right, that's science for you. On the x-axis, you're going to see the negative discriminability of these contrasts based on our calculations. And on the y-axis, you're going to see children's shaking time. In this case, it's normalized across children, but you can also use the raw data. We measured children's shaking time in 2 ways. First, from video camera, from the moment we let go of the box until the moment they made a guess. That includes their thinking time, but also we had an Arduino motion sensor in the box, so we knew how long that box was in motion. And it was a line, right? Children's exploration, relative exploration of these contrasts precisely reflected the difficulty of this discrimination problem. And I think kind of most cool, it was completely independent of the number of marbles in the box. It didn't matter if there were 2 or 4 or 9 marbles in the box. It mattered not what they heard, but what they didn't hear. What were they comparing this to? And that was what was determining how long they explored. So when I say kids' reasoning is quite sophisticated, that's the kind of thing that I'm sensitive to, right? That we're thinking about. So in the work, again, part of the project is try to take computational models of how learning might be possible and then ask what it is that children do. A lot of the early work in my lab focused on causal reasoning. We're using various models of causal inference, chiefly hierarchical Bayesian inference models. If that doesn't mean much to you, that is fine. But it basically means that you have some abstract prior knowledge, and because that acts as a strong constraint on how you interpret evidence, you can interpret it very readily. So it solves, in some sense, Piaget's problem. There are an infinity of associations, but you do not think about most of them. You come to a very quick conclusion. If I tell you a giraffe has a very long, you're all at neck right away. It could have been a trip to Kenya, right? Or, but you don't think about that, right? You converge very, very quickly on just one of the many possibilities here. So one of my students was interested in knowing whether children could use just a little bit of data to draw also an inference not about events in the world or what things like made machines light up, but about themselves, basically, and about a task, so that they could figure out their own strategy in approaching a problem. And so she was interested in persistence. And so she was comparing a case where children saw 2 bits of evidence where an adult succeeded at getting something out of a toy, but succeeded quite readily within 10 seconds, and then just repeated that 3 times, to a case where the adult struggled and struggled and struggled for 29 seconds, finally got the thing out, and had to put in a lot of effort. In both cases, babies heard but did not see, because it was under a desk, that a toy made music. We handed the babies the toy, and we looked at how long they persisted. And the poor babies, it was on a very soft felt. They were unable to make the toy make music, so we could just watch how long they tried and how long they poked it. So I'm going to show you what this looked like, because it's cute.
Look at this.
So this is the model.
There's something inside of here. I want to get my toy out of here.
This is an actual tomato container. It's super hard to figure out because actually it works from the bottom, not the top.
Do you want to see that again?
Okay. So she does this 3
Put
times.
it back in here.
I'm going to spare
How do
you.
I get it out?
And then she switches to another task where she's going to get a
I got my toy off. Do you want to see it again?
little keychain off a carabiner.
How do I get it off of here? I got my toy off. Let's see that one more time.
Okay, you don't have to see it one more time, but I'm going to show you the baby now.
Toy.
It plays music. Now you get to play with this toy, and I'll be back in 2 minutes.
So she gives it to us.
Just hand it back to her.
Okay.
Like,
3 times it's over.
this is just a quick instruction.
Good. You got it.
Right. All right. Now I'm going to show you the effort condition.
See this toy? Look, there's something inside of there. I wonder how I can get that out. How do I get my toy out? What about like this? Does this work? Can I get my toy out like this? How
All
do I
right,
get
again, I'll spare you the rest, but let's just say she struggles for a long time. And while I'm paused here, I want to say something about videos. Any 2 videos are going to differ from each other in innumerable ways, where the parent's sitting, the exact posture, all of those. We have all our videos coded blind to condition both for nuisance variables and for the target dependent measure. So what we know is the nuisance variables, differences in posture, differences in gaze back and forth between the parent, et cetera, are randomly or uniformly distributed across the 2 conditions. So they're not systematically accounting for condition differences. I can go into more detail, but for I'm pulling 2 videos, so you're going to see a lot of differences. They do not reflect differences in the samples. All right, she's struggling. She's struggling. She's struggling. And here we go.
toy? I'll be back in 2 minutes.
All right. It's really tempted to look at that second baby and really admire that baby for their persistence, but actually both babies are rational, right? We cannot try hard at everything all the time. And if what you have learned from the evidence you just saw is that something should be fairly easy, and then you try to do it and it isn't, right? Maybe this is the thing you should ask for help on, right? But if you have just seen that in this context, things are difficult, right? It even takes a grown-up a long time to do things, then it makes a lot more sense to try harder yourself. So in fact, that's what we found in both the original study and a pre-registered replication. And the important thing here is that given just 2 examples in this context, babies tried harder. They're not imitating, right? Because their task is very different from the adult tasks. And in fact, each of the adult tasks were different from each other. So they have to learn something much more abstract, which is things are hard in this room at this moment, right? It's not going to generalize to all things in the world, but they're going to draw a reasonable inference consistent with the data that they saw. Okay, I want to talk about goal-directed action more broadly. So here, this will be participatory for 1 second. Does he prefer apples or oranges? Thank you. Okay, we're really good at that, right? We can use goal-directed action to infer unobservable mental states, right? You just use the fact that this agent, presumably a rational agent, made a choice of 2 items to infer preference. And work on starting with 6-month-old babies shows that they are also sensitive to the fact that an agent's going to take the shortest path towards their goal, all else equal, they're going to engage in efficient action, and has looked at the relationship between a goal-directed action and things like preferences. But it turns out maybe it's not that simple. What about this guy? Does he prefer apples or oranges? You don't know, right? So this is a strikingly simple example, but it took about 20 years for people to arrive at this recognition. This was work by my then student and now colleague at Yale, Julian Hartinger. And he came up with a model which he called the naive utility calculus. Now, for those of you who are a little bit familiar with utility theory and economics, it turns out people are not rational utility maximizers. Very few of us will drive the 20 minutes to go check out the other car dealership, where in fact we might save a lot more money, or like in front of this car dealership, or like, oh, screw it, I'm gonna buy this car, right? So this drives economists crazy. It's a violation of utility theory, etc. Julian is now proposing that humans are utility maximizers. What he's suggesting is that our intuitive theory of a lot of goal-directed action is that we are, in fact, acting rationally with respect to utilities, which is to say, if the reward of acting exceeds the cost of acting, then we're going to act, right? And if the reward of acting, if the cost of acting exceeds the reward, we're not going to act. It's a very, very simple model, the kind you might have in an intuitive theory. But it makes a lot of surprisingly subtle predictions, right? For one thing, it predicts, for instance, if I have an action that is extremely low cost, right? I don't necessarily know how much you care about it or how valuable it is to you, right? But if something, is very costly, right? So if I drive 2 hours to the mall in order to get a bottle of shampoo, you must know I really like that shampoo. If I take the bottle of shampoo, someone hands me on the street walking out the door, you have no idea how much I like that shampoo, right? Because I would take that action under a wide range of rewards. Whereas obviously, if I'm going to take huge number of costs, right, then then I must find it very, very rewarding to do it. The same thing applies to not acting. If I refuse the bottle of shampoo, someone hands me out the door, I really don't want that shampoo. But if I refuse to follow my friend to the mall 2 hours and wait in line for the bottle of shampoo, maybe I like the shampoo, but maybe the costs of doing that are way too high. So it predicts when you'll be uncertain, when you'll be more confident, what you can infer about people's costs and rewards, and of course, the same applies in reverse. So Julian wanted to know how much this characterized the ways young children reasoned about actions in the world. And again, this is against a background of work that suggested that what you choose is what you want, right? What you choose is what you prefer. So he gave children cases. Here's Grover, and there's a cracker, and there is a cookie. And on the first trial, Grover chooses the cookie. And on the second trial, when they're set up like that, Grover chooses the cracker. And then he asks kids, what treat does Grover like best? Well, if children think that people are maximizing reward, right? If they're sensitive to reward or sensitive to choice, they should choose a chance. He chose one treat each time. But if children are sensitive to utilities, right? If they think that that you need to consider what happens when the costs are equated, what choice does he make then they should think that Grover prefers the cookies. And indeed, 4 and 5-year-olds do exactly that. They can also infer costs that way. Suppose they know that Cookie Monster really likes cookies, but Grover likes cookies and crackers equally. And then suppose you show them this setup. Here, each puppet walks into the room. It's set up like this, and Grover chooses the cracker, and Cookie Monster also chooses the cracker. And then you ask the kids, one of our friends has trouble climbing up the big box. Which one? Well, nobody tried to climb up the big box. Nobody struggled. Nobody failed, right? But you know that only Cookie Monster has a preference here, right? So if he didn't act on the reward, it must be because the costs are too high, whereas you do not know that about Grover. And by the way, we counterbalanced all these things. We had Grover and Clovers and various other things. So, so kids are very good at this. They can use the action and knowledge of the rewards to infer agents' costs. They can use action, knowledge of the costs to infer agents' preferences. But this very simple account turns to have implications for many other aspects of psychology, including pragmatics and even moral reasoning. So for instance, suppose this guy says, "Could you get me the ball?" Who's he talking to, the tall guy or the short guy? The tall guy. How do you know, right? It's an ambiguous setup. Well, you can rationally infer, right? Because the tall guy is much more likely to respond. It's very easy. It's a low-cost action, and so he'll act under a wide range of rewards, whereas the short guy would have to be like super motivated to help that blue guy out. This actually lies behind a lot of ordinary language inferences that have been puzzling for a long time. Suppose I give you this sentence, Annie should pass the salt to Claire because she's close to it. Who's she? Annie. Suppose Anna should pass the salt to Claire because she's far away from it. Who's she? That's not in the grammar. And it's not in the meaning. It is in your mind. It's in your understanding of utilities and why those sentences might make sense and how they would work. And indeed, children use this to resolve pragmatic ambiguities. You use this to resolve pragmatic ambiguities all the time. I'll show you one more. Suppose this guy asks for the ball and both these guys say no. Who's a jerk? All right. Agents who do not help at low cost, you know, are not very motivated. We exonerate people from not helping because something's very costly. We do not all have to rush out and donate our kidneys. But if you don't hold the door open for someone, that's a real problem, right? So we wanted to know if children were sensitive to these kinds of things also. And first, we just wanted to know if, at this point, this was early, whether babies, young children, were even sensitive to how costly actions were for children. So we showed them two puppets. They both succeeded activating a toy, but one puppet had to work pretty hard to get the toy to go, and the other succeeded right away. And the first question was just, which one would you rather play with? And I like statistics like this. These are 21-month-olds. They distinguished these two puppets. They would much prefer to play with the more competent puppet, the puppet who had incurred lower costs. So then, with just slightly older children, we said, okay, well, if that's true, then do they use these inferences about agents' costs to make inferences about their motivation? So we, again, showed them the same thing. One puppet succeeds easily, one struggles. And then the parent, whose back had been turned, turns around and says, can you help me play with this toy? And both puppets say no. And then we ask the children, which puppet is nicer, right? Which puppet is nicer? So again, both puppets have been sort of antisocial. They both said no, right? But they should be more likely to exonerate the puppet who had to put in a lot more effort. And indeed, that is exactly what children do. By the way, they still prefer playing with competent puppets, but they infer that the other puppet. Okay. Recently, a colleague of mine, then a postdoc at Harvard, now a colleague at Johns Hopkins, has extended these kinds of inferences to 10-month-old babies. And she has shown that babies expect the agent to incur higher costs for one agent than another, like that agent better. And she's also looked at categories of risk where agents have to jump over shallow or deep precipices, and asked if babies can make the inference. If you're willing to jump over a great big scary drop off for someone else, then you prefer that entity more than the other. These are all in looking time trials, so I can again talk about the details of the methods. But as early as 10 months, we seem to be using these kinds of inferences to make sense of human action. And I think with respect to this audience, there's just enormous potential out there in bringing together current computational accounts. This is one, but there are many others of what we call theory of mind, and perhaps in this field also, inferences about beliefs, desires, intentions, goals, actions, attention. And again, we're focusing on all the things that go right? The incredible things that human minds really can do. I mean, human minds are remarkable. We invent these fields, pretty much everything in this room. It's an extraordinarily powerful computational machinery. And yeah, as you know better than anyone, that sometimes can go tragically awry, and understanding both how the typical development works and also the many things about this complicated machinery that can break, I think is the next horizon of science. Okay, I might give one more. How's my time? 12:44. I'll do this very quickly. What are these guys looking at? Okay, but there's no baby in the scene, right? So if you were, an image, you would say, how do you know there's a baby there? There isn't a baby. How about these folks? What are they looking at? Scary movie. But again, no scary movie. If you think I swiped these off Google Images, you're right. But this was a photograph taken in my living room a few years ago. And it's the same thing, right? As it happens, these kids are looking at Harry Potter and the Chamber of Secrets at the moment the basilisk comes out. So how do you do this, right? How are you able to infer things that are not even in the scene, just looking at someone's face, right? Just looking at how they're reacting. Well, there is a probabilistic and quite nuanced relationships between things that happen in the world and how our emotional reactions, right? So this is a positive, whoops, those were scary images, but this is a positive one, right? And this is a positive one, but it's different. And this is a positive one, but it's different still. To the degree that infants are sensitive to the kinds of events and the kinds of reactions they will elicit, they recover language in the first 12 months, right? All the language. They may be able to pick up on these relationships in the environment and make inferences about the causes of people's reactions. So we asked that in an experiment here, and this is against a backdrop that, at least in my field, has had kind of two dominant theories of emotion. One is circumplex theory, which is just two-dimensional, valence and arousal. Another is 5 basic emotions, anger, sadness, happiness, disgust. We showed our undergraduates, actually, pictures. And we just asked them to make a nonverbal vocalization in response to each of these pictures. I'm going to play those and see if you can guess what people are looking at. Can you hear?
Ooh. Aww. Oh.
Wasn't that hard, right? And this, again, very fine-grained. And one of those is even a negative picture, but we expected it would elicit a positive, comforting, emotional reaction. So then we asked the same thing of babies and children, right? So we played a sound, we had the two images, and we asked which would they look at, right? So you see something like this, and you see something like this. And you just look where the babies look, right?
Ooh.
Right? And you can see if they look back and forth and how they look at the images. And indeed, again, I won't go into details, but across numerous experiments, there's a small but significant effect for 15-month-olds, I think I'm accurately telling you the age of the babies here, to look at the target stimuli across all these trials, and there's no difference between these emotions. Okay, so that suggests that they can pick up some of these associations. What about actually inferring causes, right? So in this case, the experimenter looked into a box and said, right? And pulled out, say, a fruit. Or she looked into a box and said, and pulled out a fruit. Okay, now baby gets a chance to reach into the box, and the question is, where do they search from, right? So in this case, you can't be associating the sound with a thing. There's always a sound in a fruit, right? But if you infer that there's a cause of the person's emotional reaction, right? And that is a probable cause, right? Fruits could make you say, But that is a really improbable cause of that sound, right? You probably don't say to a banana. Then children should go looking for what did make you make that sound, right? Is there something else in the box? We contrasted it with cases like this, where you said, and pulled out a teddy bear. That's really weird. You should look longer. Or you said, and you pulled out a stuffed animal. That's not so weird, right? And again, the children go searching longer. We also did it with, exciting things and cute things. And children search longer when those emotional expressions are incongruent with what's in them. Okay, so again, children are sensitive to these very nuanced within valence emotional expressions. They go searching for probable causes when they're not otherwise evident. For a long time at MIT, they moved it because they put in a big brain sculpture, but we had a sign like this out there that was perception, cognition, action, and a big blank square, which I think where emotion probably belongs. So hopefully we're starting to fill in some of the blanks there. So I'm going to end here, and I want to end first by acknowledging the children who taught me most about children, none of which is in the talk, but especially Henry for the moment, and also all the participating families, organizations, and funders. So thank you very much. And I'm happy to take questions. I'm happy to linger afterwards too if I've run time down a little bit.
This has been one of the funnest grand round sessions I think we've had in a very long time. No diss to anybody who's been here before, but
I said I was going to be the comic relief,
Well, and several of us are now plotting to leave our current jobs to become research assistants at MIT.
Don't do that. We need you.
Okay. Who in the audience here has questions? We do have one online, but I just want to scan the room first because you're right here. Oh, hey, Helen.
Hello.
Hello.
As Zipporah was saying, thank you. That was really fun. So I know that your focus is on sort of healthy, developing children, but I can't, and maybe this is the Department of Psychiatry person in me, but I guess
Please.
I'm thinking about what does this help us understand or learn about children who respond in an atypical way? Do they tend to respond atypically to most of these trials, or is it kind of specific to one of these things? How predictive is that of other things that could happen? Are there things that we learn if we know this early enough that can help ameliorate long-term challenges or things down the road? I mean, there's that's probably a whole other hour presentation and we don't have that kind of time, but just maybe broadly speaking.
And that is why you're not going to leave your jobs and come over. Instead, we're going to collaborate because we don't know, right? We don't know. These are not the kinds of tests that are used as predictive models of psychopathology, right? These are experiments that were designed to test, again, often, the computational model says, with this kind of prior information, this amount of evidence, they'll learn this kind of thing, right? So we're not using them to follow up children. We're not using them to recruit. I recruit in two ways. Until the pandemic, pretty much at the Boston Children's Museum, we had three floors on the museum floor. We were there 60 hours a week. The museum brings in 500,000 children, so it was a pretty good lab. Not nearly as good as the lab we have now. We've developed an online developmental platform called Children Helping Science, which all of you can use too. It's open access, open source. There are about 150 labs in the field on it. We now test children in their homes online, often with automated studies, not Zoom, no scheduling. The data just comes in. The parents give consent through the video camera, and we can post studies. So that is a whole different model, and it allows us, I think, to begin to look at much larger samples, much more quantitative data, but also special populations, whether that is language groups or children at risk for particular disorders and diseases. I think we now stand to learn a lot more. And the answer is right now, I cannot answer your question, but in the next generation should be able to.
Thank you. I see some questions rolling in online, beginning with thank you so much for the presentation. I'm curious, what does current research say about the earliest age that children develop theory of mind, and what facilitates their development of theory of mind?
It's a huge fight. So there was a beautiful, closest we came to Piaget and stage theory had collapsed. But there was a kind of consensus that children started out understanding knowledge and ignorance, something corvids and non-human primates understand also. They will steal food from a dominant who can't see, but not one who can. So they understand that seeing leads to knowing and all of that. But they didn't understand, was the argument, beliefs, which is to say they didn't understand you could think something was true of the world and be wrong, right? So false beliefs. That was the litmus test of understanding. It's not like pretend. They could, if you pretend something, it's not true, but you know it's not true. That's why you're pretending, right? But a false belief, you don't know which of your beliefs right now is wrong. Right? They all feel like right beliefs. We all know one of them or many of them are wrong, but we can't tell which ones they are. That ability to understand that minds are representational, we were quite sure came in around 4 and 5 and not before. I can tell you all the studies that showed that. Then someone in René Baillargeon and Karen Onishi came out with a paper in Science in 2007 that said false belief in 15-month-old babies. Since then, there have been innumerable back and forth about whether that is reproducible, reliable, what it shows. There have been many, many findings out there. So it's still very controversial, I think, about what we know about these representations. So, yeah. That's a short answer. I teach a whole set of lectures.
No, that's okay.
My colleague Rebecca Sachs teaches entire classes on this.
We have somebody here who said thank you for the baby picture of Henry. No, I'm kidding. I just added that myself.
I'll put that in the hallway.
Yes. Well, no, we're keeping that forever. So this question does speak to something that I think many of us are wondering about now. Your example of the impact of infant observing of adult effort makes me wonder about possible implications for clinical teaching. When teaching clinical techniques, the default approach is to show students or learners how it's done. I can imagine that this pulls learners to feel like giving up when their efforts don't produce the same results as what their instructor was able to achieve. Your presentation prompts me to wonder if there would be benefit if instructors instead showed their struggles in applying any given technique, including failed efforts, before finally getting it right. Might this enhance learner confidence and persistence in their learning of new clinical techniques?
I'm answering as a human, not a scientist, because obviously I haven't tested that, but I would say almost certainly, right? So I think one of the things that as experts we do, you can look at a whole list of glorious accomplishments, and each of us who has that long list knows all the times that we're like, yeah, that was a disaster and that failed and this didn't work and that was super hard, right? And I was really wrong about that one. I have a colleague who has a rejection collection that she shares with her students. So, all the bad reviews, all the things that didn't get anywhere, all the grants that got turned down. So I think that it's very easy to present to others as if the thing that we show is all there is, as opposed to showing the long history and the enormous effort and the many failures that go into it. And I think it's much more encouraging and normalizing and real to the degree that you can communicate that also. And probably does allow people to persist and not feel like, well, everyone else succeeded and nobody's ever told me about getting a review like this.
Well, I've learned also from your talk that I should either throw or eat all my failures. So thank you for giving me some new techniques. And this from our chair, a brilliant talk. Would you please provide your perspective on what seems to be cognitive overstimulation on our children from internet and social media in relation to their developmental learning? Do they accelerate or interrupt that learning?
This isn't my field of expertise, and it is other people's field of expertise. So as a parent, as Henry will tell you, I'm a Luddite. We didn't allow a TV in the house. And, my 17-year-old has been carefully educated to still allow me to have a screen time password on her phone and to time her out of things after 20 minutes. She can ask to remove them, and she does pretty much daily, but she wants it there in place because she understands its addictive potential. The research, on the other hand, is very mixed, right? Very mixed. So there are serious experts in the field who say that it is a moral panic. I do tell my students that Plato was very upset about writing because what was going to happen to our oral histories. He wasn't wrong. Very few of us can recite the Iliad. Probably zero, right? So we tend to, radio, actually the reason there isn't children's programming on radio is they passed laws. They thought radio would corrupt children. So there is PBS and Nickelodeon, Disney on TV because they didn't pass those laws for television, but they did for radio. So there's no children, or was, not until Disney radio now, but there wasn't radio for kids. So it is, I think it's very hard to tell in the middle of it. It looks awful. I mean, I hate it, right? I hate it for myself. I try to get off of it all of the time, but serious research in it have been upset about the degree to which people who are not experts in the field have been able to put their thumb on the scale and say these things are a disaster. I ban it in my classrooms, right? I think that multitasking, we have lots of evidence on, like, everyone thinks they're good at it, we're all terrible at it, right? But is it globally bad, or are we actually super smart? We're processing a lot. I think jury's out a little bit, which I hate to say because I can't stand the stuff, but that's personal. Many scientists would disagree with me, who know better.
Well, I just want to just scan and make sure I'm not missing anybody else. Oh, yes. I can't get all the way over there. Could I invite you? I mean, I can, but it would be a lot of effort for me, Kathleen.
I could walk too. I guess one of the things that I'm curious about in looking at those great examples, which are very provocative, is are there any kind of repeat studies that look at how that learning is extended if it's a familiar teacher, right? If we presume that there's an attachment relationship or an emotional connection between the teacher, kind of adult, and the effort learning by the kid. I have my own ideas that are totally theoretically based, but I'd be curious if there was an expansion of that research that was informed by attachment ideas.
What came to mind is a funny example, but I'm going to say it because I think it says something. Patricia Kuhl, who's a researcher of early language, it turns out that newborn babies can hear every phoneme on Earth. Right? So if you say cha with your tongue in the front of your mouth and cha with the tongue in your back of your mouth, unless any of you speak Serbo-Croatian, you probably don't hear that distinction, but those are two different letters in Serbo-Croatian. So there's a perceptual tuning where that you come to really hear the phonemes that are present in your language, and you lose the ability to hear the others. She looked at 9-month-old babies who were exposed to Mandarin in one of two ways. Either there was a video playing of a Mandarin speaker interacting with a child-directed speech, or there was an actual speaker of Mandarin who was interacting with the child for the whole time. Only the children who had the in-person interaction kept open the perceptual window for those distinctions. Hearing it, even though it's an acoustic signal in the background all the time, did not preserve that window. That study was not really set out to answer the question you're asking. I think there's an abundance of collective wisdom and knowledge from educators, clinicians, families, that relationships matter, that children learn in relationships. And if the relationship goes south, good luck on the learning. I can't offhand point to but again, it's not my area of expertise, it probably is yours. But I think we do need to understand a lot more about the ways that close, intimate, supportive relationships change minds, change learning. Because I think that, abundant reasons, I think that's the case.
Well, I think this group is not going to argue about how much relationships matter, but we will say with a round of applause and our gratitude, thank you so much for being with us today.